Okay, so for chapter 7, we're going to discuss the foundations of spectrophotometry. Okay, so we defined last time spectrophotometry as the study or spectroscopy, the study of the interaction of light with matter. Okay, because light interacts with matter, then we were able to make analysis methods that identify and quantify elements, okay, or compounds based on their interaction with light. Okay, so that was defined last, I think, chapter 1, okay, or chapter 0. Okay, so we defined spectrophotometry. So we will discuss it today, and let's look at some details about this field of study. Okay, so this will be our topic flow. So we will go with the review of the electromagnetic radiation, which is just a basic review of your physics, and then later on, we will proceed with the methods of analysis for spectroscopic analysis. Okay, so let's have a review on uh, the electromagnetic waves or light. Okay, so we know in physics that light exists as an electromagnetic spectrum. Okay, so we have lots of variation of light. Even our radio waves can be considered light. Okay, so the one being transmitted by our cell phone devices, they can be considered light as well, because again, light is a big spectrum. So apparently our eyes can only see a tiny portion of the light called the visible light. Okay, but majority of the light around us cannot be seen by the naked eyes because of their wavelength. Okay, it's possible that the wavelength is too big or too small, so they don't interact with the rods and cones of our eyes. Okay, so in the mm, in this end of the spectrum, we have wavelengths that are big. Okay, so we have bigger wavelengths on this side. Okay, and some of those light fall under the category of infrared light or infrared rays, microwaves, and then radio waves. Radio waves are a form of light or a form of electromagnetic spectrum that are used in telecommunication devices. Microwaves, on the other hand, these are forms of light that are used in, let's say, microwave oven. Okay? The word microwave in microwave oven refers to the microwaves being used by that device. Okay, and then infrared rays, these are used, for example, in our heaters. Okay, or sometimes in our remote controls. No? So they use infrared rays. So the characteristic of these waves on the right side of the spectrum is that they are big enough. Okay, so their wavelengths are big. Okay, so that means the distance between the two crests are big. You know? Okay, so remember, waves look like this. Okay, so if the distance of the crest is big enough, okay, so this is called the wavelength, and then so if the distance of the two crests or the two peaks are big enough, then they could either fall into this one of these categories. Okay, and then the shorter your wavelength becomes, then it starts to appear as a color. Okay, it starts to appear in the visible spectrum, and you know that red colors will come first. Okay, because this has relatively larger wavelength than those in the violet color. Okay, so as you transition from bigger wavelengths to smaller wavelengths, the color change will be from red, orange, yellow, green, blue, indigo, violet. Okay, or the Roy G B if we know. Okay, so red will have the highest wavelength for the visible spectrum, and then violet will have the shortest wavelength for the visible spectrum. And as you proceed, making the wavelengths much smaller, then you will come to a point where your waves become invisible again. And then they could either fall under these three categories again. So they could be ultraviolet, X-rays, and gamma rays. Now, ultraviolet rays, these are forms of uh, light that are emitted by the sun. Okay. X-rays, this is what we use in getting our X-ray images. Okay, so it actually can penetrate the bones of our body, giving us our X-ray film or X-ray photograph. And this was discovered by uh, Henry Becquerel and his wife. Okay. And then gamma rays, this is the most energetic form of radiation, the most energetic form of light. So this can actually destroy your skin or destroy your cells in the body. They can even destroy DNA when you got hit by gamma rays. Okay, so gamma rays are I used gamma rays in my thesis now because my thesis work on polymerization of some material. Okay, so in order for me to do polymerization reaction, I use gamma rays, and uh, we can easily obtain gamma rays from the PNRA facility here in the Philippines. Now, in Quezon City, you can apply for use of gamma rays now. Although again, this is very dangerous form of waves, but this is proven to be beneficial in some ways. Okay, so it can help us in our research field. For example, in my thesis, I used gamma rays to accomplish my thesis. We can also use gamma rays to kill bacteria. For example, the way they sterilize your gloves, the surgical gloves that we use in our homes or in hospitals, the way they sterilize that is that they pass through gamma rays on that material. And as gamma rays passes through the gloves, what happens is that it can actually destroy bacteria cell or bacterial cell. Okay, it can. I think it can even destroy viruses. I think, but I'm not really familiar. So anyway, so another characteristic of waves are this now. If you increase the wavelength, the energy or the frequency becomes smaller. Okay, so increasing the wavelength of your waves decreases its frequency. We will denote the frequency as the Greek letter nu. Okay, so increasing the wavelength decreases the frequency. So when you say frequency, that is the cycles per second of a wave. Now, how many waves can you form in a second? Okay. So for example, I have this wavelength with bigger uh, distances. Okay, so bigger wavelength, and I have this wave with much smaller distances for the wavelength. Okay, so you can see this one will have much smaller frequency than this one. Okay, suppose this is 1 second. Suppose we have 1 second mark here. Okay, so as you can see, the shorter the wavelength is, the greater your frequency will be. The more cycles you can create in a second. Okay, so the relationship of frequency and wavelength is inverse. Okay, so if you write that in equation, we can say that frequency is inversely proportional with the wavelength. So removing proportionality by introducing constant will give us nu equals c over lambda. The c is what's called the speed of light, which is a constant. Okay? So this is the proportionality constant of the frequency and the lambda. So that is the speed of light, which is, of course, we know that that's 3 times 10 raised to 8 meters per second. That is the maximum speed uh, of light. That's the maximum speed of light in the entirety of universe. No speeds can actually surpass that speed of light, except if that's dark matter. Okay, so that's another form of physics stuff. Okay, and so you have to somehow memorize this because this is important in our field as well. Okay, so you have to somehow memorize the the parts of the electromagnetic spectrum. Okay, and of course the trends. The higher the wavelength is, the shorter or the lower your frequency will become. Okay, so about light, now let's focus on light first. James Maxwell was the first one to propose that light is a form of electromagnetic spectrum. Okay, so according to James Maxwell, light is an oscillation in the electric field and in the potential field around us. So as it oscillates, then it can transfer energy. Okay. Also, Sir Isaac Newton, in the early 16th, 17th century, discovered that light is composed of different colors. Okay, so for example, you have a prism and you shine light on it. Then later on, as the light passes through the prism, then you will observe many colors, diba? Okay, so that is what Sir Isaac Newton discovered. So again, James Maxwell proposed that light is an oscillation in the electromagnetic field, so it can transfer energy. And also, according to Sir Isaac Newton, that light is composed of many different colors, suggesting that it is composed of many different wavelengths. Okay, and this is the characteristic of a wave of a light. So you have your wavelength, that is the distance between the two peaks or the two troughs. Okay, so the highest point is called the peak, and the lowest point is called the troughs. Okay, and then the distance between the two consecutive peaks are called the wavelength. When you say frequency again, that's the number of oscillation you can make in a portion of a second. Okay, so the higher the portion of a second, the shorter your wavelength becomes. Okay, and then we got this equation. Uh, Nu equals c over lambda, or cross multiplying lambda, we get lambda nu equals c, the speed of light. Okay, and by the way, lambda is wavelength, and nu, that's a Greek letter, that is frequency. Okay, so there were no there early in 19th century, there were mysteries about the behavior of light, which causes huge or dramatic shift in the field of physics. Okay, so there were several phenomena that they can't explain before, and that caused more discoveries about matter and light. Okay, so the first one to discover the weird behavior of light is Max Planck. So according to Max Planck, light energy is quantized. Okay, so that means it comes into packets of energy. That's why we have the energy levels in the periodic table. Okay, so according to Max Planck, light is quantized. It comes in integer forms, which we know as our primary quantum number, the quantum number n. Okay, so the equation to be used in the quantization of energy is delta E equals h nu. Okay, so according to Max Planck, the energy of a particle is directly proportional to its frequency. Okay, so that is directly proportional to its frequency. Uh, Introducing a constant will remove the proportionality, and that constant is called the Planck's constant, which has a value of 6.63 times 10 raised to negative 34 joules second. And earlier, we know that frequency is the ratio of the speed of light and the wavelength. So we can plug it into this equation, giving us another equation, which is h nu I mean hc over lambda. Okay, so we can plug the earlier derived equation into this equation, giving us hc over lambda. Okay, so we can express energy in two forms. It could be in the h nu form, or it could be in hc over lambda form. Okay, okay, these two energies are the same. Okay, so according to Max Planck, light is quantized. Okay, so that means it comes in discrete packets. Okay, and the packets of light, the packets of energy is what we know as the principal quantum number n. Okay, that's the energy levels of our atoms. The next mystery about light and matter was the photoelectric effect, which was explained by Albert Einstein. And Albert Einstein won the Nobel Prize for this. He didn't won the Nobel Prize for his theory of relativity, because the theory was not yet explained before, not well discovered or not well observed before. So he didn't won the Nobel Prize for that. Instead, he won the Nobel Prize for this phenomena called the photoelectric effect. So what happened here is that Einstein investigated on the behavior of light and matter. So according to the photoelectric effect, so suppose you have a metal here. When you shine light on it, then it can actually eject the electron out of the surface of the metal. When electrons are ejected on the surface of metal, that is called the photoelectric effect. Okay, if you connect this in a series of if you connect If you connect the two, suppose you connect this metal into an electrode, and then you introduce another electrode here. If you connect that, then you can actually create a cell potential. If You can actually create a cell potential out of this. Okay, so that is the photoelectric effect. According to Einstein, light can apparently cause the electron to uh, get it can cause the electron to be ejected from the metal surface. Okay, and from this he won the Nobel Prize. Okay, so this suggests that light can behave as a wave and also as a particle. And light as a particle, when it hits this, then it can push the electron outwards. Okay, because of their momentum. Okay. So anyway, to that's more explanation can be done here, but that's to physics na eh. Okay? So yan. So this is our review of light. So we started with light being as an oscillation of electromagnetic spectrum. And then light is composed of many colors according to Sir Isaac Newton. And in the development of quantum mechanics, we discovered that energy is quantized for the light. So we have this equation, E equals hc over lambda, or h nu. And then Albert Einstein explained that light behaves as a particle as well. Okay, the dual nature of light gives us uh, sorry. So the dual nature of light is the foundation of spectroscopy, because again, as you can see, light can interact with matter. Okay, so this is the foundation of spectroscopy, the photoelectric effect, because based on this based on this based on this study, light can really interact with the particles or the atoms in our molecules or in metals. Okay, so that is the foundation of the spectroscopy. So by doing some chemical reactions, or by doing some physical reactions, no, we can measure or identify elements with the interaction of light and matter. Okay. So that's our quick review of the physics. Okay, so again, that's too much physics, but we have to know the foundation of this topic kasi, no? Okay, so again, the main foundation of this topic is the dual nature of light, because apparently light can interact with matter. Okay, so with that idea, we created the new field of science, or the new field of study, called the spectroscopy. So spectroscopy is the study of the interaction between light and matter. Okay, and we know that light and matter interacts because of the photoelectric effect, which was explained by Albert Einstein. And we use spectroscopy to do measurements, which we call spectrometry. So spectrometry is the measurement of the light interaction to obtain information about your matter. Okay, so in spectroscopy, there are three things that could happen. Okay, so number one is that uh, we do emission spectroscopy, wherein we observe the behavior of light, the behavior of matter when you introduce energy into it. Okay, so when you introduce energy on your matter, then something could happen. Okay, so it could emit energy as well. Okay, so one example of this is that when you heat metals, you are introducing heat to the particles of the metals. So when the heated metals increase in temperature, what happens is that they emit light. Okay, so for example, you heat your metal. Suppose you have iron rod. So heating iron rod will make it glow. Okay, and if you characterize the glow of your sample, then what you're doing is called the emission spectroscopy. So in emission spectroscopy, you are introducing energy to your sample, and you study the emissions of that sample based on the energy you provided. Okay, so basically in emission spectroscopy, your sample glow when heated. Okay, so suppose you heat sodium chloride, so it will glow as yellow color. So that is the characteristic of sodium metal. They glow as yellow. For example, you heat copper in copper wires, it glows as green color. Okay, so depending on the characteristic of the color they emit, then you can study it thoroughly to identify the elements or to quantify them. And that field of study is called the emission spectroscopy. Okay, so one form of emission spectroscopy is the chemiluminescence. Okay, so this is a phenomena wherein based on chemical reactions, they can produce light. So one example of this is the glow stick we use in the glow sticks we use when we were young. Okay, so you break that glow stick and then light will suddenly come off from the reaction that's happening inside. Okay, so this happens because there is enough energy for the molecules to actually glow. Okay, so they can emit colors. So that's chemiluminescence. In biological species, in animals, there are animals that can exhibit chemiluminescence, and that's called the bioluminescence. There are some aquatic species and some land species that can produce light. For example, yung fireflies, okay? So they can glow, diba? So what happens inside them is that there are just some chemical reactions happening inside their body, which produces light, okay? So by studying the light produced by this species or by matter, by studying the light they can produce, you are actually doing emission spectroscopy. You can characterize the elements present in that light, or you can quantify the elements or the molecules present based on that light properties. Okay? The other form of spectroscopy is called the absorption spectroscopy. So, for example, you have your sample here. If you pass through an incident radiation onto it, it will absorb some energy. So that's why it's called the absorption spectroscopy. So what happens is that your sample will absorb some of the energy, and then the transmitted energy will be lower than your incident radiation. By getting the ratio of the transmitted and the incident radiation, you can get the absorbance. Okay, and absorbance is used to quantify. Oops, sorry. Napindot lang yung home. Let me check kung... Ayan. So, yan. By determining the ratio of the transmitted light and the incident light, getting its negative log will give us the absorbance. Okay? And in absorption spectroscopy, the absorbance of light is directly proportional to the concentration of your matter. Okay? So later on, we will have an equation which we will use in absorption spectroscopy. Okay. In photoluminescence, what happens here is that emission and absorptions happen at the same time. Okay. So suppose you have an incident light here. Okay. So once it is absorbed by the sample, then it will start glowing as well. Okay. So this is evident in materials such as the glowing materials in our bedrooms when we were young. Okay, so how they work is that they absorb light in the day. So they absorb the energy from the sun during the day, and at night they emit that energy. Okay, so that is the photoluminescence spectroscopy. Okay, so by the way, you may ask, uh, how do light interacts with matter? No? How do light interacts with matter? So according to Niels Bohr, which is the father of spectroscopy, and Einstein's explanation on the photoelectric effect, the reason why we can measure the properties of our matter based on their interaction with light is this. So according to Niels Bohr, that our electrons are in certain orbitals, right? And according to Einstein, if you have light, it can actually interact with the particles of our atom, for example, electron. So when light is passed through our atom, it can actually excite the electron. And once the electron gets excited, it goes to a higher energy level. If that electron relaxes, then it will emit light as well. Okay. So again, what happened is that when you have light or you have energy provided to your sample, what happens is that the electrons can actually get excited. And as they get excited, they go to higher energy level. And once it relaxes, once it goes back to its original energy level, it emits light. So that's the foundation of emission spectroscopy. The excitation and relaxation of electron produces light. Okay. In absorption spectroscopy, what happens here is that uh, you have your electron here. So if you pass light onto it, it gets excited. Okay. So yeah, and so it absorbs energy. However, it does not emit energy because the light we use here is not too energetic. Okay, it's not too energetic. Okay, so it just absorbs the energy. So our electrons in the sample uh, transitions from a lower energy level to a higher energy level. So in photoluminescence spectroscopy, the same thing happened with the emission spectroscopy. So light excites the electron to a higher energy level, and then as that electron relaxes, it glows. It emits light as well. Okay. So that's the foundation of spectroscopy. Basically, the interaction of light with matter, especially electrons. Okay. So going back to absorption, um, I just said earlier that the absorption or the absorbance of light of our sample is directly proportional to its concentration. Okay, so based on that, we can quantify the matter present in our sample through absorption. The equation to be used there is called the Beer-Lambert's law or the Beer's law, or basically the absorption. So according to this equation, the absorption of light is directly proportional to the concentration of our sample. Okay, so the higher the absorption of light, the higher the concentration of the sample is. But the lower absorption of light, that means the lower the concentration of your sample is. Okay, so this is what we use to quantify chemicals present in our sample. Okay, so if they are highly colored, that means they have high absorption. So if they are faintly colored, that means they have low absorption. And of course, the higher your color intensity is, the higher the absorption will be. That means the greater your concentration is. So the lower the absorption, that means the fainter your color is, the lower the concentration is. Okay. So those are the relationships between absorbance and color and concentration. Okay. So in absorption law or Beer-Lambert's law, there are some things that we have to know. First one is the transmittance. So when we say transmittance, this is the ratio. This is the ratio um, of the radiated light and the incident light. Okay. So this is the transmitted light after light passes through the sample, and this is the incident light. So that is transmittance. And if you want it to be in percentages, you just multiply the ratio by 100. Okay. So again, P is the transmitted light and P naught is the incident light. Okay. So suppose you have your sample here. So this is your incident light, and because of the absorption, the transmitted light will be much lower. So getting the ratio of the two will give us transmittance. If you get its negative log, then you have your absorbance. So again, absorbance is the negative log of transmittance, or in equation 4 that can be written as negative log P over V naught. Okay. So that means the higher the transmittance is, the lower the absorbance, and the lower the transmittance is, the higher the absorbance. The relationships are opposite because of the negative sign in front of the log function. Just like pH, the higher the pH, the lower the H plus, the lower the pH, the higher the H plus. Okay, the inverse relationship arises from the negative sign in the logarithmic function. Okay, so when we have high transmittance, that means almost all light passes through the sample. That means only few light were absorbed by the sample. Okay, and that makes sense, right? Okay, if only few light passes through your sample, that means you have lower transmittance because most of the light is being absorbed by your sample. Okay, and then if we have low transmittance, then that means we have higher absorption. Okay, because if only few light passes through this sample, then we know that most of that light is absorbed by the sample. Okay, so this is the illustration for the incident light, and this is the radiated or transmitted light. So getting their ratio will give us the transmittance, and getting its negative log will give us the absorbance. By the way, this equation is same as negative log P over P naught. So they are the same. Because according to logarithm, if you take the inverse of the fraction, according to algebra, that can be written as P naught over P raised to negative 1. So if you get the inverse of this, that's basically the inverse of the number here. Okay. Okay. So if you if you bring down this exponent in front of the log function, then you will get this positive version of the equation. Okay? Teka lang. So the two equations are the same. Okay? What just happened is that they brought down the negative exponent of the ratio in front of the log. No? And that is allowed because of the properties of logarithm. Okay? So these two equations are the same. Okay? So, yan. Okay. So anyway, this is what happens in our sample. So this is our sample container. So this is your incident light, and then light will be scattered here, and then they will be absorbed by the molecules in here, making the uh, transmitted light much lower than the incident light. Okay. So again, earlier I told you that the absorption or the absorbance of light is directly proportional with the concentration of your matter in your sample. We can write this in equation form by removing proportionality constant. We will get A equals A, B, and C. Okay. So A is the absorptivity constant, which is intrinsic property of matter. So this is unique for each type of substances. They have their own absorptivity constant. And B is the path length of your sample. This is usually in centimeter units. Typically, that's 1 cm. Okay. And then C is, of course, the concentration of your substance. Okay. If we convert this equation into molar form, mole equations, okay, so that means we are getting the molar concentration, then we get this equation. We will have this equation A equals epsilon BC, wherein epsilon is the absorptivity constant, but in terms of molarity. And the concentration now is in terms of molarity as well. Okay, so this is the equation that is used to quantify the amount of matter based on the absorption of light. Okay, so by the way, the path length should be fixed, because if you have higher path length, then your absorption will be very high. Okay, so because what happens if you have high path length is that light will interact more with matter. Okay, so that causes increase in absorption. Okay. So the higher the path length is, the higher the absorbance is as well. And the same thing for concentration. The higher the concentration is, the higher your absorbance as well. Okay. So they are all directly related. So let's try to answer this problem. Suppose we have a 7.5 times 10 raised to negative 5 molar solution of potassium permanganate. And it has a transmittance of 36.4% when measured in a 1.05 centimeter cell at a wavelength of 525 nanometer. Calculate the absorbance and the molar absorptivity of the solution. Okay. So for us to get the absorbance and the molar absorptivity of the solution, there are two equations that needs to be used. Okay. So the first one is the absorbance in terms of the transmittance. So that's A equals negative log of T. Okay. So to get the absorbance, all you have to do is to just get the negative log of your transmittance. However, the transmittance should be converted in decimal form. So it should not be in percentage. So you have to rewrite your transmittance as 0.364. Okay. So you have to convert your percent transmittance into a decimal form. Okay. Just basically divide it by 100. Okay. So getting its negative log will give us an absorbance equal to 0.439. So that's the absorbance of our samples. It doesn't have any units. It's just a number. Okay. So this is just a number. So we're done calculating the absorbance. So that's just very easy. All you have to do is to just plug in the transmittance. Okay. So the next problem is to calculate for the molar absorptivity. The equation to be used here is the A equals epsilon BC, wherein epsilon is the molar absorptivity, B is the path length, and C is the concentration. Okay, so the problem already gave us the path length of the cell and the concentration of the sample. So basically, all we have to do is to rewrite this equation as epsilon equals A over BC. And we already solved for the absorbance earlier, that's equal to 0.439. The B, or the path length, is 1.05 centimeter. And the concentration is 750 times 10 raised to negative 5 mole per liter, or molarity. So the value of epsilon, or the molar absorptivity, is 7.5 times 10 negative 5. Okay, so the value of molar absorptivity is 5574.60. Okay, so that's the value of the molar absorptivity. Its unit will be liter per mole centimeter. So this is the unit of the molar absorptivity, liter per mole centimeter. Okay, so what just happened is that I get the reciprocal of this fraction. So the liter will be now in the numerator. And on the denominator, you have the mole and the centimeter there. So this is the value for the epsilon. And again, the epsilon for each compound is different. Okay. So if you have KMNO4, it will have this epsilon value. If you have potassium dichromate, it will have a different epsilon value. If you have chlorophyll, then it will have a different epsilon value. Okay. So the epsilon value is intrinsic property of matter. Okay. So that is a constant for each sample you have. Okay. So that's the answer. Okay, so there are certain limitations with Beer's law. Uh, Number one is that if your concentration is very high, then it will start deviating from linearity. Okay, so that means Beer's law can be only applied in very dilute solution. That's why the concentration here is 10 raised to negative 5. So the concentration is very dilute because, again, at higher concentration, Beer's law starts to deviate from linearity. Okay, so as it deviates from linearity, then we cannot use the equation A equals epsilon BC. So uh, it is required when you use Beer's law to dilute your sample. Okay, so you have to dilute your sample by adding a solvent. Okay, so it could be water or organic solvent. Okay, so another limitation of the Beer's law is that when your sample reacts with light. Okay, so when your sample reacts with light, so for example, upon the introduction of, let's say, UV light, then it starts polymerizing. Okay, so that's a problem with Beer's law, because in Beer's law we assume that light doesn't react with matter. It interacts, but it doesn't causes any chemical reaction. Okay, so that's the assumption for Beer's law. We assume that light will not cause or will not initiate chemical reactions for our sample. Okay, because if that happens, then what will happen is that the molar absorptivity will change, giving us different results. Okay, it will give us different result. Okay, so those are the limitation. Again, this will only work if we have dilute samples. Okay, so that means the concentration is very low. Okay, and of course, you should take note that your absorbing species must not undergo any chemical reactions. Okay. Another limitation to the Beer's law is that the presence of stray light, when you say stray light, that is the light from the environment. It could be from the sun, could be from your uh, light bulb, it could be from your cell phone. Okay, so if stray light interacts with your sample, then it will cause errors in the measurement. Okay, so that means when using Beer's law, when using this in experimental in experiments, then it should be dark, no? So that stray light won't interfere with our measurements. Okay, and we don't have to worry about this too much because the instrument we use here, for example, the UV-vis spectrophotometer, the instrument we use here already has a container lid. Okay, so it has a lid, no, to prevent the stray light from coming in. So this is the lid, no? So you just close it to prevent the stray light from interfering our sample. So you will use this in the future. Some of my friends that are medical technologists use this in quantifying samples as well. So that is not only used in chemistry but also in medtech. Okay. So and the presence of stray light will affect the measurement. So all you have to do is to close the lid. Okay. Also, mismatched sample cell. So this is a form of personal error actually. Of course, if you place a wrong sample in the cell, then it will give you false result. Okay. This is due to personal error. Okay. This is personal error. Okay. So again, this is the graph of the Beer's law. So as you can see, as the concentration gets higher, then it starts to deviate from linearity. And because it starts deviating from linearity, then we are suggested not to. I sorry, not the guy. Excuse me. Anyway, so since the graph starts to deviate at higher concentrations, then we are expected not to exceed concentrations greater than this times 10 raised to 3. So we are expected not to exceed concentrations greater than this because it will start deviating from linearity. Okay. So assuming that our uh, by the way, so assuming that our absorbance is linear with concentration, then we can do some linear interpolation here. Okay, so later on I will give you a problem with regards to linear interpolation of the concentration given certain absorbance. Okay, so later on we'll get back to this one. So anyway, if we graph the absorbance of light depending on the wavelength, we will get what's called an absorption spectrum. So the absorption spectrum is also unique for every chemicals. Okay, so that's unique for every samples we have in the laboratory. So this is how it looks like. So this is the absorbance, this is the wavelength. So at different wavelengths, as you can see, our matter can absorb uh, different wavelengths. So it can absorb higher wavelengths at this. It can absorb much of the wavelength here and that. Okay. So again, the absorption spectrum is intrinsic for every particle. So it has a uh, unique characteristic for per sample. Okay. And also, the higher your concentration is, what happens is that the intensity of absorbance increases. Okay. So the intensity of the absorbance increases as your concentration becomes much higher. Okay. By the way, as you can see, this sample absorbs maximum light here at this specific wavelength. I'm not really sure what is the value, Well, let's assume that's 530 nanometers. Okay, so let's assume that the point at which we have the maximum absorption is 530 nanometer. This point is actually called the lambda max, and the lambda max is the point where this is a point where we have the highest absorbance. Okay, so that is the point where we have the highest absorbance. Okay, and it has to be reported. That has to be reported. So that's why in the previous problem, as you can see, we stated there that the wavelength is 525 nanometer, and the reason is that we have to state the lambda max. So this is the lambda max, no? The 525 nanometer. Okay, so that is the point wherein your sample will absorb light um, at much higher intensity than the other wavelengths. Okay, so why is that they absorb specific wavelengths? Okay, so why is that they only have one lambda max? Okay, so the reason for that is the color wheel. Okay, so the color wheel. So in physics, we know that the light we perceive in our eyes is the opposite light they absorb. Okay, so for example, you see plant that's colored green. Okay, so plant is colored green because it reflects green light. However, it absorbs the complementary color. Okay, so according to the color wheel, if our sample is green in color, then it will absorb the red light. Okay, so that means if your sample is green, then you will absorb red colors. So you will have your lambda max in this portion on the right side, because on the right side, on the higher wavelengths, you will have your red color. Okay, so if you have a green sample, then you will expect that the color is somewhere here, or the lambda max is somewhere here. Okay, that's because of the color wheel in physics. Okay. For potassium permanganate, that's actually purple in color. So that means if it is purple, then it will absorb yellow light. Okay. And yellow light has wavelengths around 500 nanometers. So this is the yellow region. Okay. Which is consistent with our graph. Okay. So since potassium permanganate is purple, then according to the color wheel, so if we have a purple sample, then it will absorb yellow light. Okay, and the wavelength of yellow light is somewhere in 500 nanometers. Okay, so if you check that in your UV-Vis, in your absorption spectrum, then you will see that the color wheel is really consistent with the experimental data. Okay. So that means depending on the color of your sample, then you can predict where your lambda max is, no, where the maximum absorption is. Okay. So this is a graph about the light absorbed and the light transmitted and the corresponding wavelength of the absorbed light. Okay. So for example, you have an orange sample. So if you have an orange sample, then you will expect that the absorption maximum is around the wavelengths for the blue color. Okay. So if you have an orange sample, then you will expect the absorbed color will be somehow colored blue. And these are the wavelengths that correspond to this color. Okay, so for example, you have red colored solution. Okay, so if you have red colored solution, then it will absorb green colors. And the wavelength for the green color is this one, 490 to 500. Okay. So depending on the color of your sample, okay, just get its complementary color, and then you can predict what the lambda max will be. You can predict where the lambda max is. Okay. So that means if you have a red sample, then it will the lambda max will be somewhere in the green color or in the green wavelength. Okay. So if you have a blue sample, then you will expect that the lambda max will be around orange wavelength. Dito pala yung orange. Yan. So you will expect that the lambda max will be somewhere in the orange wavelength. Okay? And that's the purpose of this color wheel or the complementary wheel. Okay? So the color transmitted by your sample uh, is complementary with the color it absorbs. Okay? So when you say complementary, that is just its opposite color in the color wheel. Okay. So we can simplify this as this. Okay. So you can write it as rho G B V. Okay. So this is what we use. So if you have a blue color, then it will absorb orange color. If we have a violet color, then it will absorb yellow color. If you have a red colored sample, then it will absorb green color, and so on and so forth. Okay, so you can use this as abbreviation for whatever this thing is. Okay, so this is the shortcut method for this one. Okay, so again, the purpose of this color wheel is for us to know what is the lambda max, where the maximum absorption will be. And according to the color wheel, the maximum absorption will be on the complementary color of your sample. Okay. And now let's go back with the Beer's law. So suppose you are doing chemical analysis. Now you want to quantify your sample. How are you going to do that? Okay. So we can use the Beer's law to actually create a standard calibration curve. We actually skipped this part in chapter 2. Okay, so in chapter 2, I discussed the calibration curve. This is a graph wherein we can do linear interpolation of x. Okay, given the known value, given the y value, we can get the x value. So we can do linear regression here. Okay. However, we will try to simplify linear regression. We will not do any statistical stuff anymore. Rather, we will use technology to solve for that. Okay. So standard calibration curve is the plot of the concentration versus absorbance. In your vertical axis, you have your absorbance, and on the horizontal axis, you have your concentration. Since according to Beer's law, direct ang relation ng... Ay, bigla nagtagalog. Since according to Beer's law, the concentration is directly proportional to the absorbance, then we can assume that the relationship is linear, provided that the concentration is not so concentrated. The concentration is not so high. So the relationship is linear. Okay. So if we know a specific y values, then we can get x values. But before we do that, you have to establish the linear calibration curve first. Okay. So let's try this problem. So suppose you have these concentration values, and these are their corresponding absorbance. What is the concentration of the sample if this is the absorbance? Okay. And suppose you're given this data, then you have to interpret the concentration of the sample given this absorption data. So we have two ways to do this. No? We can use the calculator to do linear regression. And later on, I will show you how to do this in Excel. Okay. So I hope you have your Excel with you. Okay. So please open your Microsoft Excel later. But for now, I will do the calculator technique. Okay. Okay. So let me, yeah, let me. So if your calculator can do statistical functions, so please follow me. Okay. Clear ko lang. Okay. So to access the statistical function of your calculator, especially if that's Casio 991 ES plus, Casio 570, uh, or Casio 570 ES. Okay, so if you have those variants of calculator, then you can access the statistical function by clicking Shift and the mode. Okay. Ay, sorry, hindi pala yan. Sorry. You can access the stat function by clicking just the mode. Okay, just press this button, mode. So as you press the button, you will be given lots of options. You have your statistical function here, the equation here. Remember, we use this in equilibrium, right? Okay. So, but now we are going to use the stat function. We use this in statistics in chemistry, right? Okay, so I hope you still remember this. So press 3 to access the stat function. And then you will be given lots of options. You have your one variable. This is what we use in determining the standard deviation, the mean of our sample set. Okay. However, if you want to do linear regression, you have to press this button here, the number 2, which stands for a plus bx. So this a plus bx is the linear regression mode of your calculator. So just select that uh, mode. Okay. So now your screen will look like this. You have the x column and the y column. Okay. So in Beer-Lambert's law, the x is the concentration and the y is the absorbance. Okay. So the x is the concentration, the y is the absorbance. So all you have to do is to plug in the known values of the concentration and their corresponding absorbances. Okay. So allow me to type this first. Okay. So you type in the concentration on the x-axis and the absorbance on the y-axis. So we have 0.005. Okay. Oh, sorry. And then the absorbance of that will be 0.217. I have 0.01 concentration. The absorbance is 0.432. If I have a concentration of 0.015, then I will have an absorbance of 0.641. And then lastly, if I have a concentration of 0.02, I will have absorbance of 0.0867. Okay. So all you have to do is to plug in all the known concentrations, plug in the known concentrations and their corresponding absorbance value. You have to exclude this part, huh? Because it doesn't have any defined x value. Okay, so just only this part. What we're actually doing here is this. Okay, what we're doing here is this. We are actually plotting in the calculator the equation of a line. Remember in mathematics, in geometry, 2 points define a line. However, in this problem, we have 4 points. Okay, so that will help us define a good calibration curve. So these points will be graphed by our calculator. Okay, and then later on, given that graph, we can get its equation, y equals mx plus b. Okay. Okay, so by plugging in the concentration and the absorbance, then we can get the equation of the line later. Okay, that is what your calculator is doing. Okay, it creates it creates a graph. Okay. Okay, so for us to know the equation of the line, press AC. Okay, press AC. Okay, so after you press AC, nothing will be shown in the calculator. Then press shift and the stat. Okay, stat is above this button 1. Again, you press AC, you press shift, then 1, then you will be shown this menu. Okay, in this menu there are lots of options. You have your variance, you have your standard deviation here as well, but we don't need that. Rather, we need the regression data. So you press 5 for the regression data. Okay, so as you press 5, you will be given another sub-menu. So you have your A, you have your B, you have your R, you have your X hat, and the Y hat. However, we are only interested in A, B, and the R. Okay. So what is B? Okay. So B is the slope of the line. Okay. Remember that the calculator uses the format y equals bx plus a. So that means whatever the B is, that is the slope of the line. Okay. So let's identify the slope. Okay. You press 2 and then you press equal sign. So this is the slope of the line. So we have y equals 43.18 x. To get the intercept, you press AC again. You press shift stat, then you press 5, and then you press A. Okay. So again, B is the slope of the line. The intercept is the A. You press 1 and then you press equal sign. You will get this intercept. 5 times 10 raised to negative 4. So now we have an equation of the line and we can use this to get the unknown concentration of our sample. That's how you create calibration curve in the calculator. You just use the stat function, and then you get the B as your slope and the A as your intercept. Another important thing for us to get is the value of R, or the R square. When we say R, that is the Pearson correlation coefficient. Now remember your statistics. According to statistics, the Pearson correlation coefficient tells us how related our values to one another. Okay, so if you have a graph that looks like this, then we can say the R value is low, no? Okay, meaning there is no relation or there is no correlation between the y-axis and the x-axis. So it has a very low R. However, if your data points look like this, then we can say we have a high correlation value. Okay. Okay. So remember your statistics, no? When we do linear regression, we always check for the R. So the value of R ranges from 0 to 1. So the more it approaches the value of 1, that means the relationship between the two variables can be established. However, if you have low values for R, then you cannot establish good relationship between the two variables. Okay? Okay, so remember your descriptive statistics. Huh? So anyway, you already knew that because you discussed that in senior high school naman. Okay. So anyway, so again, it is very important for us to get the value of the R square or the Pearson correlation coefficient. The higher the value is, the more linear our relationship is. That means we can continue solving for the problem. Okay. So again, to access the Pearson correlation coefficient, you just press shift, stat, then regression, followed by 3, which is R. And of course, you have to square it. You have to square it. Yan. So this is the Pearson correlation coefficient, which is 0.99975. That is actually a very good coefficient. Of course, it will be somehow impossible to get exactly 1 as your Pearson correlation coefficient. So it is somehow possible to get that. Why? Because of experimental errors. Okay. So, yeah. So it will be somehow impossible to get a correlation coefficient equal to 1. Okay. But it is possible, no? It is possible, but on a very rare occasion. And actually, on my thesis, no, I actually got R equal to 1. So my graph was really linear, no? So I I'm looking for that graph. But yeah, so in my thesis, I was actually able to get an R value equal to 1. Okay. So I was actually amazed when I got that result. No? But anyway, in typical experimental cases, then we really don't get uh, R exactly equal to 1 always. And that's not the result always. Okay. I think this is my calibration curve where I get the R value equal to 1. Nahanap ko lang ha. Wait lang. Wala. Nabura ko yung data. But anyway, uh, I actually deleted the data, but this is how it looks like. Okay. This is how the calibration looks like. This is atomic absorption spectrophotometry. I use that to quantify lead on my sample. So this is what we're actually doing. So you are plotting the x values and the y values. Then you get the equation of the line. And this is the equation of the line. Absorbance equals slope concentration plus the intercept. And then this is your Pearson correlation coefficient. Okay. I somehow deleted the um, my r square being equal to 1. But I think I got it printed. Anyway, so yeah. Anyway, so getting r square equal to 1 is somehow very impossible to do, but it can be done. Okay. So the goal in chemical experiments, the goal is to get at least an R value of 0.999. If you get this 3 consecutive 9s, then that means your calibration is good. Okay, you can proceed doing the analysis. Okay. So, as you can see, this one has a lower R value, 998, but this is still acceptable. Okay, so one of the reason why it has a lower R value is because of this point. Okay, at this concentration, it is somehow deviated from linearity. Okay, so you can actually do test for outliers here. You can test the out if this is an outlier. Okay. Anyway, so going back to the problem, we now have the equation of the line, then we have the Pearson correlation coefficient, which we found out to be acceptable because it has 3 consecutive 9 values. Okay, so we can use this equation now to get the concentration of the sample. Okay, so let's get the concentration of the sample. Remember that X stands for the concentration and Y stands for the absorbance. So let us solve for the X using this equation. We have Y equals 4318x minus 5 times 10 negative 30 negative 4. You transpose the intercept on the other side, so it will now become positive, and then you divide both sides by 43.18 to get the x value, to get the concentration. So now what's left for us to do is to plug in the absorbance, and then we will get the sample concentration now. Okay, so just plug in the absorbance here. So that's 0.724 plus 5 times 10 negative 4 divided by 43.18. So that will give us the value for x, which is the concentration. 724 5 times 10 negative 4 43.18. So the concentration is found out to be equal to 0.017. So that is the concentration of your sample. Okay. So it is somewhere between 0.15 and 0.20. Okay, because the absorbance value is in between these two. Okay, and then we got this value, which is which is between these two concentrations. Okay, so that's how you solve for the concentration given your calibration curve now. So again, all you have to do is to get the concentrations, plot it against the absorbance. You plot it, then you get the equation of the line and the r square. So if you have an r square equal to this and 3 consecutive 9s, then you can proceed doing your calculation. Okay. So you have your given absorbance, that's the y. Then for you to get the x, all you have to do is to manipulate the equation. Okay, so we manipulated, we transpose the intercept to this side, we divided both sides by the slope, then we get the x value. Okay, so that's how you do it in the calculator process. If you want to rewatch the method, then just wait for the video to be uploaded. Okay, on Microsoft or Microsoft OneDrive or in YouTube. Okay, so just rewatch this part of the video. Anyway, so that's how you do it in the calculator. However, if you don't have a calculator that can do that, you can use Excel, no? Because you are on your computer naman. No? So let's do that in Excel. So in Excel, you just open a worksheet. You type here the concentration and the absorbance. So allow me to type the values. Okay. So this is our data. Okay. This is our data. You have your concentrations here, and then you have your absorbance here. So to get the equation of the line, all you have to do is to highlight the concentration and the absorbance. By the way, your concentration will be on the left, the absorbance will be on the right, because this will serve as the x-axis. This will serve as the y-axis. So to get the equation of the line, all you have to do is to highlight your cell. Highlight your cell. Go to insert. And on the charts, you can see this last menu here, which is the scatter plot. Okay. So you go to insert, then you go to the charts option, then you will see scatter plot here. Okay. So you press that, and then you choose this one, the scatter plot. Okay. So by choosing that, I will get this. Get this graph. Okay. So I will get this graph here. So what's next is that you click one of the circles there, one of the data points. When as you click the data points, then you will see that your data are highlighted. Okay. Anyway, so click one of the data points, press right click. Okay. So again, click the data point, right click, then choose add trend line. Okay. So as you can see, a line has been established. Okay. So as you create the trend line, make sure that your trend line is linear, because again we are doing linear regression here. You should choose this, not the others. Okay. So scroll down, you will get into the two last option. You can get the r square and the equation. So you just check those boxes. So you will get this equation of the line, which is the same as what we got earlier. This is the slope, 4318. This is the intercept, -5 times 10 raised to -4. And this is the r square. This is rounded off, however. This is 0.9998. What we got is 0.99975. So if you round this off, you will get 0.9998. Okay. So this is just rounded off. So that's how you do linear regression in your Excel. Then once you have the equation of the line, all you have to do is to manipulate it to get the x value. Okay. You just transpose this, divide both sides by the slope, then you will get the x value. Okay, so that's how you create the trend line. So again, let me do it very quick na lang. For the last time, highlight your data, go to insert, choose the scatter plot, and then once you have the scatter plot, click one of the data points, press right click, add trend line, choose linear. Okay, and then scroll down, you will get, you have to check those two last boxes. Check the equation and check the r square. Now you will get an equation of the line. Okay. However, it is highly suggested that you can do this in your calculator because I'm not really sure if you will use this in your board exam, but maybe, okay, maybe. So maybe you need to establish calibration curves in your clinical chemistry, which is a board subject. So it will be highly suggested if you know how to do that in your calculator. But for now, since we are in online setting naman, you can use Excel if you don't have a calculator that is capable of doing stat function. Okay, so that's how you do it. Okay. So that's how we analyze our samples using calibration curves. Okay, so we're almost done. So now let's talk about the other forms of absorption. So we're done with the calculations. So let's proceed with other concepts na lang. So let's talk about the absorption data. So there are many types of absorption data. One of one of which is the atomic absorption, which gives us an idea about the absorbed energy of the atoms. Okay, and this is what I used in my thesis. I used the atomic absorption spectrophotometer, or AAS. So basically, what we analyze in AAS are elements, okay? Typically metal ions. So what happens here is that you will feed the instrument with metal ion solution, and then it will start analyzing the absorbance of that metal ion um, as it becomes combusted. Okay. So in atomic absorption spectroscopy, you are determining the atoms, okay? And the atoms sample, the atom concentration, or the atom identity, okay? So this is how it looks like, and this is how it looks like. Uh, atom. So this is how the AAS looks like, the atomic spectrophotometer. So you have this instrument, you will feed your, so this is your metal ion solution. Then you will feed it in your igniter. So the liquid will be combusted, and then, as we know, metals produce different colors, right? So it produces different colors. So based on the color intensity and the color of the flame that is produced when you combust your metal, then you can quantify them. So this is what I used in my thesis. No? Okay. So when you operate this, it's quite hot. No? It generates a lot of heat. No? So even though you have an air-conditioned room, you will feel the flames talaga, because what you're doing there is you literally burn your samples. Okay, so that's AAS, or atomic absorption. You are quantifying atoms, especially metal atoms. Okay. So for molecular absorption, these are the modes of absorption. When our light energy, so it could be ultraviolet, visible, or infrared, or microwaves. No, so if those waves passes through our molecules, there are many modes of electronic transition that happen in them. Okay, so there could be vibrations. Okay, so for example, this is a water molecule. When it is influenced by an electromagnetic radiation, it starts to vibrate. Okay. Okay, so there are many modes of vibration. Could be symmetric, asymmetric. Anyway, you don't have to memorize this. Ah, okay. And the electronic transition of the molecules are not so energetic, no? So that means the transition will be from low energy level to another low energy level. Okay, so it's not so high for infrared. However, for UVVs, the transition of the energy levels of the electrons will be much higher. Okay. So because again, infrared has lower energy than ultraviolet and visible light. Okay. So the transitions for infrared will be just lower energy levels, but for UVVs, that will be higher energy levels. Okay. So for emission spectra, so this is the line spectra. This was actually used by Niels Bohr to prove his quantum theory. Okay. So Niels Bohr is the father of the quantum mechanics, and he used the line spectra. According to him, for each element, there is a unique line spectra for them. Okay. Then using the line spectra, then we can measure or we can identify the elements present in a sample. And this is what the physicists are using to determine the composition of stars, no? To determine the composition of exoplanets. No? So this is what they use in determining the elemental composition of those celestial bodies. So basically, what they will do is that they will focus their telescopes for say in a star. Okay, so they will focus the telescope in a star, and then they will observe the spectral data that is emitted by the atoms that are being burned in that star. Okay, so by collecting the spectral lines, then they can identify the elements. Okay, so for example, for our sun, this is how the spectral data looks like for the sun. Let me pull it out from the data from the internet. So, for example, you have your sun, which is in the middle of the solar system. This is how the spectral line looks like for the sun. Okay. So this is how the spectral data looks like for the sun. Okay. Okay, so this is a better picture because you can see the elements here. So this is what the physicists are doing. Okay. So they have the spectral lines. They will focus the telescope on a celestial object, and they will observe the spectral line, and then from that they can identify the elements present in that star. Okay. For example, the sun is composed of hydrogen, calcium, iron, magnesium, sodium, oxygen, and other elements. Okay. So our sun contains iron na, no? So that means in the next few billions of years, the sun will explode, okay, because it contains iron already. Okay, so when the star contains iron, then later on in its life cycle, it will become supernova. No? So sasabog yung star natin because it already contains iron. Okay. Anyway, so that is what they use in identifying the elements present in celestial objects, the line spectra. We can also use this thing called the band spectra to identify the molecules present. I mean to identify the bonds present in molecules. Okay, so we use the band spectra to identify the bonds present in the molecules. And let me give you an example of that. So let me pull up my thesis presentation. Okay. So this is my thesis presentation. That's my thesis. I made this material as an adsorbent for lead. So I actually used the gamma radiation facility of the Philippine Nuclear Research Institute now. So this is how my material looks like. So before it is liquid. So with the help of the gamma radiation, uh, it was converted to a polymer. Okay, and I use this polymer to absorb metals. Anyway, for band spectra, we use that to determine the bonds present in the molecule. So for example, this is the molecule acrylamide. So if you subject it uh, to infrared rays, no, to infrared rays, then you will get this spectral data, the band spectra. Okay. So as you can see here, this can be interpreted as the NH2 bond. This peak here can be interpreted as the carbonyl bond. This peak here can be interpreted as the double bond there, and these other peaks in there can be interpreted as all the other single bonds in there. Okay, so when light interacts with my molecule, it will start vibrating and it will produce this type of graph. Okay, so another example will be this one, polyacrylamide. So for example, we interpret this as the NH bond. However, the intensity was decreased because it was a new bond was formed. Okay, so this can be interpreted as this. Okay, okay. For glucose, we interpret this as the OH bonds. We have this peak here. We interpret it as the C single bond O bonds. Okay, and then this is the gel which I have. We interpret this peak as the combination of the uh, amine and the hydroxyl group, so on and so forth. Okay, so that is what we use in chemistry to identify the bonds present in the sample. Okay, so this is very important for us, especially for you as well. No? In the future, maybe some of you will go in research industries, so you will encounter these instruments again. Okay. So that's band spectra. We use that to identify the bonds present in molecules. Okay. And then we have the continuous spectra. So this one is used in physics. When you hit objects, they glow, and the glow is a characteristic for every element. Okay. So if you graph the glow of the curve, if you graph the glow uh, of the metals, then you will get this graph now, the continuous spectra. This was also used by physicists to prove quantum mechanics is real. Okay, this was used to prove that quantum mechanics is real. Anyway, if you're interested with that, you can watch a BBC documentary about that now. But for now, let's just skip that. Okay, so for fluorescence spectra, again, when you say fluorescence, the atoms or the molecules will fluoresce, meaning they will glow. Okay, so for example, this is the atomic fluorescence, which is similar with the atomic spectra, the line spectra. Okay, so for molecular fluorescence, there are two forms of fluorescence. For non-radiative relaxation, there is a vibrational, deactivation, and internal conversion. Anyway, we don't have to uh, discuss them any further because these are too, ano na, these are too technical na. But again, just the overall idea. Na. Okay. We're just getting the overall idea for this topic. Okay, so again, fluorescence. This is the excitation of electrons in a molecule wherein they start to glow. Okay, so these are the excitation of the electrons to different energy levels, which we will not also discuss in details, because this is too technical. Okay, so we're done. So that's the foundation of spectrophotometry. So before we end our session, let's have a short recap of what we did. So the first thing we understood was the understanding of light. No? So before they said that light is just an electromagnetic radiation. However, due to quantum mechanics, we were able to establish that light can interact with matter. And according to Albert Einstein, uh, the light has a dual nature, light as a wave and light as a particle. Okay, this dual nature of light enables us to quantify matter depending on how it interacts with light. Okay. So there are many types of spectroscopic methods we use in chemistry. We have the emission spectroscopy, wherein you absorb wherein your sample will absorb energy and then it will start emitting colors. Okay, so depending on the colors they emit, you can identify the elements present there or you can quantify them. And then you have your atomic absorption. In atomic absorption, what happens here is that your sample will absorb the light energy to convert it from a ground state to a higher energy level state. Then by getting the ratio of the transmitted light and the incident light, you can get the absorbance. Okay. And then for photoluminescence or the fluorescence spectroscopy, what happens here is that the combination of emission and absorption happens at the same time. Okay. So the thing that we use in the laboratory often is the absorption spectroscopy, which follows the Beer-Lambert's equation or just simply the Beer's law. Okay. So again, transmittance is the ratio of the transmitted and the incident light. And if you get its negative log, you will get the absorbance. The higher the transmittance is, the lower the absorbance. Of course, it is logical because if almost all light passed through the sample, then that means only few of them were absorbed. Okay, so the inverse relationship of the two is logical. No? And that's given by the negative sign in the log function. Okay, so according also to Beer's law, the absorption or the absorbance is directly related to the concentration of your sample. So if you have a higher concentration sample, then that means it will have higher absorbance, of course, because there are more molecules that will interact with the light, hence more absorbance. Okay. Also, path length will play a role. Okay, so that's why it is kept constant, because if you increase the path length, then that means light will pass through much more particles. No, so you have to fix. You have to let this path length to be constant. Okay, in molar form, the Beer's law can be written as the epsilon BC, wherein epsilon is the molar absorptivity. And this is intrinsic property for matter. So each type of molecules will have their corresponding epsilon. Okay. So we can actually identify molecules based on their epsilon. Okay. You can actually look this up in Google. Okay. So in Google, you will see a table full of epsilon values for different compounds. Okay. So there you go. We answered this problem. We just converted transmittance to absorbance, and then we got the epsilon. And then later on, I ask you what's the meaning of this. Okay, so this is the lambda max. This is the point wherein the maximum absorption will happen. And according to the color wheel, the absorbed color is the complementary of what we see. Okay. For example, if we have a red sample, then its absorbed color will be the green. So that means its lambda max will have a green value. So to get their exact values for the wavelength, you just look at this table. For example, if you have a blue sample, then it will absorb yellow color, which has wavelengths around here. For potassium permanganate, it is purple. So it will absorb this color, and this is the corresponding wavelength for that. Okay. So which is consistent with our example here. Because again, I told you that potassium permanganate is purple, so it will absorb anong color nga ba ina-absorb? So since it is purple, it will absorb wavelengths at around orange color, no, or wavelengths from 500 to 550 something. Okay, so as you can see, the wavelength is inside those color range now. Okay, so that is true, and that is experimentally observed now. Okay, so in quantitative analysis, what we do here is that we establish a calibration curve wherein we create an equation of the line that relates the concentration of the species being investigated and their absorbances. Now, by creating the calibration curve, then we can get the value for unknown concentrations given their corresponding absorbances. Excuse me. Earlier, I have shown you how to do this in calculator. So it is suggested that you can do this on it is highly suggested that you can do this in your calculator without relying on Excel. However, if you don't have any calculator that can do this, yeah, you can rely on Excel na lang. Okay. So, and then these are the other forms of spectra. We have the atomic spectra. What we measure here are atoms. Okay. And then here we have the line spectra, same for atoms, but in emission mode. This is the fluorescence, atomic fluorescence, which is similar with the atomic spectra. Okay. Anyway, so let me before I end, let me just explain to you what happens in microwave ovens. Okay. So what happens in microwave oven is that the molecules will undergo vibration transition. Okay, so when you turn on your microwave oven, okay, it starts to emit microwaves, no? Kaya nga siya microwave oven. And that's why it's called microwave oven, because it produces microwaves. Okay, so when microwaves hit the water molecules in your food, what happens is that the energy of microwaves causes the water molecule to start vibrating. So these are the modes of vibration for the water. Okay. So once it start vibrating, so imagine your hands are the water molecules. Okay. So when you start vibrating your hands, or basically just rub your hands against each other, it starts to heat up. Okay, so that is the concept behind the microwave oven. So what happens there is that the microwave will interact with water molecules, and because of that interaction, the water molecules will start to vibrate, and the vibration of water molecules causes the temperature to increase. Therefore, your your food will be heated, no? Heated to your desired temperature. Okay, so that's the application of this topic at home. Now you can use your microwaves with the help of quantum mechanics. Now, with the help of Albert Einstein, you can do that. Now, so we are so thankful for them, especially to Niels Bohr, because without Niels Bohr, quantum mechanics will be a failure. Okay, but Niels Bohr persisted. No, actually, let me just tell you a quick story. Even though Albert Einstein explained the photoelectric effect, no, the reason why Niels Bohr was called the father of quantum mechanics is that because Niels Bohr really pushed that idea. Albert Einstein resisted Niels Bohr's idea, the Copenhagen interpretation or the quantum mechanics. Okay, so he actually refuted all the claims made by Niels Bohr because according to Einstein, in his own words, it is illogical. However, it is proven that quantum mechanics is true and we can apply it in our homes, diba? In microwave ovens, it is true, no? So yeah, so the point here is that even smart people aren't always correct. Okay, so they aren't always correct. One example would be Albert Einstein. He refuted the quantum mechanics, but in modern science, no, modern science is not complete without quantum mechanics. No, so yan lang. So not because you're smart, you're always correct. No, okay. So Albert Einstein died without believing in quantum mechanics, but in reality, quantum mechanics allowed us to discover lots of stuff around us. No, so it allowed us to discover how to heat foods with microwaves. No, for example. Okay. So that will be the end of chapter 7. Uh, Let me go back to our Canvas account. Okay. So before I end the session, again, yeah. So again, take note of the calendar. We are on the second week prior to your final exam. So please take note of that. You should not waste any time. Okay. Should not waste your time for matters that do not matter that much for now, no? Although yes, you can of course prioritize your your rest, no? Even I prioritize my rest din naman, no? So last time I actually had an exam, but yeah, tulog is life, no? So you have to rest so that your health will not fail you, okay? And then other than that, you must start realigning your focus to your finals, okay? uh, it is highly suggested you stop binge watching muna, no? You stop watching Netflix muna and focus on the upcoming finals, no? So the earlier you get prepared, the better, no? Okay. So anyway, so we're done with this chapter. Next week we will have a synchronous session. I will upload the material maybe around Tuesday or Monday. Okay, because this weekends I have lots of stuff to do. Okay, but I will make sure I will upload the material on Monday or Tuesday. Okay, so that will be the last discussion for this semester. Okay, tomorrow I think I need to move this now. So I will move this to Monday na lang, same as this one. So on Monday, I will upload the quiz for chapter 7 and chapter 8. And I will allow you to take that quiz for um, a longer period of time now. Okay, so I will allow you to take those two quizzes for a longer period of time. Okay, but before, ayan. And what else? Ano pa ba kailangan ko sabihin? Ayan, so just be prepared for your finals. And then again, the material for this lesson can be found here. Okay, in the lecture module, you will find this PowerPoint here. Okay, so please download this chapter 7. By the way, for those asking where the worksheets are, they are in the announcement tab. Okay, so look, just check the announcement tab and go to here and go to this post, additional resource material. Here you can find the worksheets. Okay, so I update this every now and then for chapter 7, I will also upload another worksheet focusing on the linear calibration curve and the calculation for the absorbance and the um, epsilon, okay, or the molar absorptivity. Okay, so if you have any questions, please let me know. Sir, okay lang po ba mag-open ng tab for Excel? Yes po. If you don't have a calculator that can do stat function, then you can open your Microsoft Excel. Okay, that's allowed, no? Especially if you don't have a calculator that can do linear regression. Yeah. So yes, you can open your Excel in the quiz and in the examination, especially if there is a calibration problem there. Okay. So, do you have any other questions, Papa? Because this will be the last time you will see me after this. You will only see me on YouTube na lang. Okay. By the way, so I would like to take this time to thank you all for being so being so masipag. uh, for being uh, for being my student for this semester, no? Especially to those to to your classmates who have been with me since the beginning of time. So yeah, I would like to thank you for your efforts in this subject. I know that analytical chemistry is a very, very, very hard subject, no? I know you know that, 'di ba? Kasi it has lots of calculations in it, no? But you persisted, no? And apparently most of you still got um, good scores, no? And that's a sign that you are really doing well. So I'd like to congratulate you for that. And yeah, so I really appreciate you. Some of you asking me even at night, no? So hindi siya hassle for me, no? So kasi nakikita ko yung effort niyo, no? I can see your effort even gabi na you study the subject, no? So I really appreciate that, no? So to my former students, and to my new students this semester. So this will be the last time you will see me because in your biochemistry, I am not the instructor there anymore. There are other biochemists in FEU that will teach the subject matter better than me. Okay, so that means this will be the last semester I will be handling you. Okay, so yeah, so thank you very much for being with me for a short period of time now, and I hope that in the future we will see each other again face to face, no? So in FEU. So and so that will be all. So thank you very much for being um, for for everything, no? Wala lang. Nagdrama pa, no? Wala lang kasi wala, bakasyon na naman eh. Summer na naman eh. You know naman, pag summer, wala tayong ginagawa, no? So, ayan. So, I really appreciate you, no? Especially sa mga former students ko, no? Uh, and they really chose me talaga to be their Anachem prof, no? For example, si Gian, yan. Student ko yan dati. I think si Nina din, student ko dati, no? Si Krisha, yan. Mga student ko dati. Okay, so yan. So thank you for entrusting your lives sa akin for this semester, no? So anyway, so we're still not done yet, no? Pero ayun, so this marks the end of the semester na rin. Although hindi pa talaga tapos yung ating discussion, we're not really done with the chapter. Pero yun nga, so this will be the last time that we will see each other as synchronously, and I hope that one day we will see each other face to face. No? So for now, please stay safe and always and yun, wala na akong masabi. So yun, so for now, please stay safe and uh, have a great day and good luck in your upcoming finals. So if you have any question, please do not hesitate to ask me. By the way, my upcoming project for the summer is that I will be creating YouTube videos as your reviewer for your battery exam next year. So I will be creating YouTube videos as a reviewer for your battery exam next year. So please watch out for those videos. Na? So I'll be updating my YouTube channel again this June, July. Okay. So yeah, so that's all. It's almost time. So thank you and God bless as always. I'll see you again very soon. Okay. So thank you and